Hello, I'm Kelsey Lindberg. I am a traffic engineer with SRF Consulting Group based out of Minneapolis, Minnesota. Collin?
Yeah, hi everyone. This is Collin Schroeder, also with SRF based out of Minneapolis. And yeah, so we'll be talking to you today about how we used VSIM for the Iowa Crossroads dual rail in transload study. Just before we begin, I'd like to acknowledge our project partners for this effort. We worked with the Iowa DOT, Webster County, Iowa, as well as McClure Engineering for this project. Alrighty, so for today's agenda, I'll first discuss the project background, then I'll dive into the future conditions and talk about what exactly triggered this study. Then I'll talk about the project goals and the alternatives that were developed and evaluated to accommodate the future conditions. Then I'll pass it off to Kelsey, who will walk through how we used VSIM to achieve those project goals and to talk about some of the evaluation criteria that was included as a part of this project. And then we'll close it out with some model visualization. This is something that really helped the client understand what the operations of the facility and the project area may look like in the future, and proved to be a very useful tool for us in the overall process. So a little bit on the project background. The project area is located in Webster County, Iowa, shown in the map on the right here, just west of the city of Fort Dodge. The project site is a 1,000-acre transload facility that is comprised of 3 operating facilities. There's CJ BioAmerica, Cargill, and Valero. And the map on the bottom right shows the site highlighted in red relative to Fort Dodge, just to the east there. And you can see just kind of the different railroad, the rails that is kind of feeding into that project site there. So currently on the site, employees and trucks access the facility using State Highway 7. In Highway 7, just a little bit of the traffic characteristics of Highway 7. It carries about 3,500 vehicles per day based on 2023 traffic data with a posted speed of 55 miles per hour. So there's not a lot of traffic on the roadway, but there is a good amount of heavy vehicle activity on Highway 7 and in the area, which is primarily due to the facility. So with high speeds on Highway 7 and trucks turning in and out of the facility, that's something that we wanted to keep in mind when evaluating alternatives for this project. So zooming a little bit further into the project site, the current facility is highlighted in blue there in the map below. And it is bounded by Highway 7 to the north, a Union Pacific line to the east, and a Canadian National line to the south. The project area consists of 4 side street stop controlled intersections, all along Highway 7. These locations were chosen for analysis because they are either current or planned future access locations to the facility. And there is 1 at-grade rail crossing under the existing conditions with Highway 7 and the Union Pacific line at the northeast corner of the facility. And so the existing site has about 250 trucks in and out per day. And the trucks take about 15 to 20 minutes to circulate within the facility and ultimately leave. It's also important to note that based on the data that we collected, the current operation of the facility has the highest truck activity during the morning peak hour. So the truck peak and the vehicle peak are aligned on Highway 7 in this area. So just another thing to just keep in mind, trucks turning in and out, truck volumes are the heaviest along with the vehicles. So just making sure we're accommodating those movements safely. Then there are about 10 trains per day on each track. So it's not a whole lot of train activity, but some of these trains can be up to 2 miles in length and traveling at about 30 to 40 miles per hour. So this can result in crossing times at that existing at-grade crossing of up to 4 minutes. So that further introduces more delay for vehicles and trucks. All right, so the future conditions of the site, there are plans to expand the transload facility, which essentially doubles the acreage of the existing site. So this plans for expansion is what triggered this study right here. So as a part of the expansion, the Highway 7 alignment has been proposed to be realigned further to the north, noted by the blue line in the map there. This realignment would essentially result in that old Highway 7 alignment to kind of function as a CD road for trucks entering and exiting the facility. So this takes the trucks turning in and out of the facility immediately and puts them at 2 access points on Highway 7. And allows them to access this facility away from that Highway 7 mainline traffic. So the facility expansion would also add 2 rail crossings on the existing Highway 7 alignment. And if the Highway 7 were to be realigned, there would be 1 rail crossing on the proposed realignment. All right, so continuing with the future conditions of the site here, the facility is set for expansion in 2027. So that would be our year of opening for this analysis. The facility expansion results in an additional 350 new jobs, 250 truck trips per day, and 10 additional trains on the track per day. So basically with the acreage doubling of the existing site, the truck trips and the trains would also double in the project area as well. And so in addition to this near-term expansion, there's also an additional 400 acres that are preserved for future expansion. So this led us to evaluate a year 2047 scenario as well, on top of that year of opening. And so just to account for some background growth on Highway 7, we used a 0.5% growth rate, which was determined based on historical traffic data on Highway 7. All right, so with the understanding of what this site may look like in the future, and I think the main project goal is to understand what the impact the expansion has in this project area, and to also come up with different alternatives that accommodate that expansion. So there has been some concern with the internal track loop crossings and the impact that it would have on the Highway 7 through traffic. So that would be one of the primary focuses of this project here. And we also wanted to evaluate the performance of different alternatives just to best accommodate the operations and the expansion of this existing condition. So using performance measures from VSIM, we were able to conduct a full benefit cost analysis, accounting for the operating costs of the expansion, as well as the travel time costs for each alternative. So with those goals in mind, we coordinated with the project team to evaluate and develop 4 different alternatives. The key features to each of these alternatives included the Highway 7 alignment and the rail crossing grades. So the 4 alternatives just included kind of various combinations of those 2 key components. And as I mentioned previously, the alternatives analysis included the year of opening 2027, as well as future year 2047. So these scenarios would account for that near-term known expansion and the potential for that long-term expansion. And this would also supplement the 20-year traffic analysis period for the benefit cost analysis. So now going through the 4 different alternatives that were developed and evaluated. This is the first alternative that was developed, and this is essentially just kind of the do nothing scenario. So this alternative uses the existing Highway 7 alignment and leaves all those track loop rail crossings at grade. The benefit of this alternative is it's very low cost. However, this leaves the truck traffic accessing the site on the main line, and it also leaves the Highway 7 traffic conflicting with the rail crossings at 3 different locations. And with the train activity doubling on the project site, this could lead to a lot of additional travel time as well as some safety concerns with these being at grade. So the second alternative kind of builds off of that first one. It's still using that existing Highway 7 alignment, but this one includes grade separation between the 3 rail crossings with the track loops and that Union Pacific line. So the pros of this one, the Highway 7 traffic does not conflict with the rail. However, this one still leaves the truck traffic accessing the site on and off of Highway 7. It's also high cost, and there were some engineering and safety challenges getting the bridge clearance up and over the rail crossings and then back down to grade to accommodate the access points on the site. So the third alternative now includes that realignment of Highway 7. However, this one still leaves all those rail crossings at grade. So the benefit of this one is that realignment really takes that truck activity off of Highway 7. However, there's still the at grade rail crossings. So there's still those conflicts. Some potential for delay and increased travel times, as well as some safety concerns. And it's relatively high cost. The realignment and grading, the realignment presents some grading challenges, especially at that new crossing. And then the fourth alternative is very similar to that third alternative. However, this one just includes that grade separation with a bridge over the rail crossing on the new Highway 7 alignment. So again, this one taking that truck traffic off of the Highway 7 main line, and Highway 7 traffic does not conflict with the rail. However, again, similar to alternative 3, the grade separation at that rail crossing does kind of solve some of those grading issues that we were facing at that new crossing. There is still some additional costs for the construction of that bridge as well. And so now I'll pass it to Kelsey to talk about how we used VSIM for this project.
So when we were determining which software was the most appropriate to answer the questions that our clients had, VSIM was identified very early on as the right tool for the job. The ability to really dive down into the details of how this model runs made VSIM super flexible to model the realistic rail operations, as well as the truck operations within the transload facility. It also allowed us to create visualizations of the model to effectively communicate results to the client, as well as create visuals for their own benefit for their marketing purposes. So given the main factor of the rail versus vehicle and being able to model the rail as realistically as possible was crucial. So each crossing was individualized to match either the existing or the design rail operations. And this included matching the train lengths and the operating speeds of the existing UP line, as well as the planned train lanes and operating speeds of the internal lines. And this was used to determine the crossing duration at each crossing. We also used RBCs in order to model the gates with the train detection, abiding to the Federal Railroad Administration's minimum warning time of 20 seconds in order to capture a more realistic delay for the vehicles as they're waiting for the train to cross. As part of the project, the truck traffic was extremely important to model correctly. We wanted to ensure that we did not overload the intersection with trucks returning back to Highway 7 earlier than they would normally. So while the grain trucks were set to arrive stochastically throughout the AM and the PM peaks, with the cargo train deliveries completed prior to the PM peak, extra consideration was made for the truck departure rate after they were through the facility. This was done using a 3-step process, with each step being controlled with a stop sign, each with their own time distribution based on real-world durations. So upon entering the site, each truck stops on the initial weighing station for approximately 20 seconds and then loops around and unloads their grain. This 3.5 minutes is a typical value. This is highly dependent on the type of truck and the type of infrastructure at the facility for unloading. We chose 3.5 minutes as a typical value. And then once they leave the grain unload process, they hit a final weighing station for an additional 20 seconds, where they can now loop around and enter Highway 7 again. So the evaluation criteria that we pulled from VSIM for this project, including the vehicle crossing delays at each crossing and the corresponding maximum queues of these vehicles. We also analyzed the corridor travel times for the realignment versus the existing alignment for the through-to-through vehicles, as well as the network performance, including the VHT and VMT, to support the benefit cost analysis. In the year 2027, there was not a lot of variation expected under each alternative when it came to the crossing delay. By 2047, the alternative 1 was beginning to stand out as having additional delay due to the combination of the truck and vehicle crossing and all crossings being at grade. You'll notice that there is no alternative 2 in this one. Alternative 2 was not analyzed with rail crossings, as all crossings will be grade separated. By 2047, it was anticipated that all alternatives would result in maximum queues from the crossings interfering with adjacent intersections. However, the primary concern of the client was the interaction of the rails with each other. So none of the alternatives were anticipated to result in queuing that would cross an adjacent rail crossing. So no alternative stood out as a fatal flaw for the vehicle queuing. For the existing travel times, according to Google Maps, during both the AM and the PM peaks, the existing corridor travel time for both the eastbound and the westbound through-to-through vehicles is approximately 6 minutes. We selected alternative 1 as our base comparison for each alternative, given how close it is to the existing alignment as is. One of the concerns of the client was the introduction of the out of direction travel for realignment of Highway 7. Through the analysis, it was determined that all alternatives, with the exception of alternative 1, results in a reduction of travel time compared to existing. And it was even interesting to note that the realignment of Highway 7, even with the additional travel distance, still resulted in a reduction in vehicle travel times as compared to existing, due to the removal of the interactions at the intersections with the trucks and with the higher travel speeds possible on the realignment. For the network performance, results were fairly similar among each alternative. Highway 2 had some obvious benefits for vehicle hours traveled due to the removal of interaction with all rails. However, it didn't provide much benefit for the vehicle miles traveled. The benefit for the alternatives 3 and 4, which is the realignment, were pretty consistent with the alternative 1, just due to that extra travel distance kind of offsetting some of that benefit. And to support the benefit cost summary, VSIM was used in the user and societal cost. The vehicle operating cost and the emission costs utilized the VMT from the model, with the travel time cost using the VHT. And then the crash cost utilized the existing rail versus vehicle volumes at the crossings to analyze the vehicle exposure in terms of safety. Alternatives 2 and 3 both had a negative net present value, with alternative 4 being the only positive net present value. It's just interesting to note that even with the grade separation of alternative 4, it still had more benefit than alternative 3. This was primarily due to the topography in the area with the proposed rail crossing on the new realignment, and the cost to get that intersection at grade was more expensive than constructing the grade separation. One of the final outputs of the model that we requested by the client was a visualization, a series of them, in fact. They wanted a accurate visual of what the queuing would actually mean in relation to the existing intersections and the other rails. This visualization that I am playing now was one of the ones that they had requested for their marketing purposes. So this right here is the west crossing under the realignment, and it will transition to the transload facilities to show how the trucks will move through. It was specifically requested by the client to include 3D objects into the visualization, which was a big perk of using VSIM. Because in the end, this was a marketing material for their future expansion to 2047. Any questions?
All right, thank you very much for the presentation.